is, what is it? It is r squared. I'm saying this has radius r, by the way. R squared sine phi, and then I usually rattle something off like d phi d theta rho hat. Well, that's great, but what is rho hat? Well, all right. So the integral of f dot ds, the flux of this vector field z hat through this sphere, hemisphere rather. So let me say hr, hemisphere, radius r. Upper hemisphere. Put a plus on it there. Now I feel better. Whatever you want to call it. I don't know. I feel like this hemisphere is not good. There you go. No Mets fans? No? All right. My dad was big into Mets when I was little. Anyway, there, that's a better name. Less writing, Mets. There we go. We'll call this hemisphere the Mets. Sorry, I'm on a sort of ridiculous naming phase today. So you guys tell me what, I'll do the easy part. Theta ranges from 0 to 2 pi, right? How about phi? I mean, up here, we have phi equals to 0. What's this base phase? Phi equals to what? Pi over 2, right? So we have integral 0 to 2 pi, integral 0 to pi over 2, and then we've got this pesky r squared sine phi d phi d theta. We got to figure out what on earth this rho hat dot z hat is, yeah? What is rho hat dot z hat? What is rho hat? Remember, rho hat is the unit vector in direction of increasing spherical radius. So we've worked this out before. It's exactly cosine theta. It's cosine theta sine phi, sine theta sine phi, cosine phi. That vector points to the unit sphere in the direction of phi and theta. Well, for your choice of phi and theta. So when we look at rho hat dot z hat, what is that actually? Right, this is nothing more than cosine of phi. And so the integral we actually face here is the integral from 0 to 2 pi. Well, first of all, I can pull the r squared out. And then I've got integral from 0 to 2 pi of d theta. Integral from 0 to pi over 2. Looks like we got a cosine phi, sine phi d phi, yeah? And at this point, you got various choices for the integration. How do you want to do it? We could do u substitution. We could remember that 1/2 of sine 2 phi is equal to sine phi cosine phi. That one's kind of fun. So if we do that, then this gives me 2 pi r squared, minus 1/4 cosine of 2 phi, evaluated from 0 to pi over 2. See, because that's 1/2 sine 2 phi, and then making a u equals 2 phi substitution, I generate an extra factor of 1/2. Anyway, my larger point here is if you differentiate what I wrote down, you get back to 1/2 sine 2 phi, I think. And so evaluate what we got. 0, you say. Is that right? I get 1/4. Yeah, it's 0. What? It gets 0? No. That ain't right. I mean, that's not right. Yes? All right, yeah, let's be, man, that's kind of different, right?
Minus 1/4.
Okay, so yeah, we got 1/4 from the upper, and then, oh, minus, yeah, I forgot. Phew, I tell you what, be careful. You guys almost talked me into 0, which would have just been preposterous. Looks like, oh, check that out. Pi r squared, what do you know? Does this make any sense? All right, so what we're talking about here is the unit vector field, right? So with field lines, I don't know if I'm doing it very well, but not really. My point is any field line which goes through the units, the hemisphere, it also cuts through the disk. But the thing is, you know, the normal to the hemisphere is what? Like this, right? So, I mean, if the vector field lined up with the normals to the hemisphere everywhere, it would just be the surface area of the hemisphere times the surface area of the hemisphere. For example, if I was to calculate the flux integral over the upper hemisphere of not this vector field, but let's say rho hat dot ds, well, that would just give me 4 pi r squared divided by 2. I can tell you that from just direct geometric reasoning. The rho hat vector field lines up with ds, right? So every field line counts. Every field line has magnitude 1, so the flux is just surface area times magnitude, which is 1/2 of the total surface area of the sphere. But what's different about z hat is it doesn't line up with the ds, right? But what's the significance of the pi r squared? Yeah.
It will probably be on your first physics test.
It will probably be on your first physics test, yes. This is the kind of intuition that evil physics good, well-meaning physics instructors try to test you on. See, because the point is that the flux here, it's as if, well, how to say this? Somehow these two pieces cancel and only the upward part of the flux remains in the flux integral, if that makes sense. In some sense, only the z, for every part of the surface that's pointing to the left or to the right, there's a left part, there's a right part, those cancel out in the integration. There's a back, there's a front part, those cancel out in the integration. What remains is the z part of the flux. That's the only part which is not canceled out as you sum around the sphere. But anyway, it's not an accident that we get pi r squared for the answer, because that's the area of the disk, right? And certainly if you look at the flux of the z hat vector field through the disk, that's quite clearly pi r squared times the magnitude of z hat, which is 1. Because z hat does exactly line up with the normal to the disk. So there's one. So my larger point here that I was trying to make, somewhat clumsily, is that we could calculate the flux of like a subset of our standard examples. For example, you could calculate the flux through something like, let's see here, here's one. Suppose we want to take this sort of half pipe. I don't know if this is actually a standard example, but I can write down what the parameterization is here and tell you. So suppose I want ds to be like this. So here's x equals to 0. Let's say here is, y equals to 0. Here over here is, let's say, y equals to 1. Let's say h. So if you understand the intuition for this problem, if I gave you the vector field f equal to z hat, right, and said find the flux through this thing. Could you tell me what it would be? Yeah.
It would be the flux through the area of the square that covers.
Yes, exactly. It would be, and so if I, oh, I haven't told you enough, have I? So let's suppose that that distance is w. It would just be, you know, h times w times the magnitude of that, which is 1. Yeah. Because if you look at it like this, there's a ds here like that. There's a ds here like that. And as you look at z hat on the different sides, the part which is left and the part which is right, they're going to be canceled as you sum over all of them. There's a symmetry there. There's a cancellation going on. Only the z hat component remains. And anyway, sorry. So don't mean to get too far off track on physics type comments. And tomorrow, I will hopefully tell you the major theorems. Thanks, guys.